Hello, welcome again. In this video, we're gonna discuss how to find the cardinality of GL and ZP. So we need to explain what this GL and ZP is. So first of all, ZP, well, some people write it down, or actually the more proper way to write this set, the integer modulo P is Z mod P, something like that, right? Which means that 0, 1 up to P minus 1, where the addition and the multiplication is taken as the addition and multiplication modulo P, right? And GLN is the set of n by n invertible matrices. So when we write down GLN ZP, it means the set of n by n invertible matrices where all the entries are coming from the integer modulo P. Okay, so I hope it's clear that what this set is. Okay, so now we want to count the cardinality of this GLN, right? So remember, we have the following fact. Well, it is a fact if you know it already, but if you don't know yet, you perhaps would like to prove it. Okay, which says that a matrix A is invertible if and only if all its columns are linearly independent. Okay, so then in this case, a matrix is in GLN if all the columns of this matrices, all these columns of this matrix forms linearly independent vectors. The vector columns are all linearly independent. Okay, so let's take a look for a simple case. Let's see, for example, GL2, right? GL2 ZP. Okay, so remember that we would like to have a 2 by 2 matrix so that the column vectors are linearly independent. So how can we choose two column vectors that are linearly independent? Okay, so first of all, we can choose for the first vector, first column can be any vector but the zero vector. Why is that so? Because if we have a zero vector, then the set of the vectors is certainly not linearly independent. Okay, so the only column, the only vector that we cannot choose for our first column is the zero vector. Okay, so now since we are allowed to choose any column vector but the zero vector, then we need to think of in how many ways we can do such thing. So for the first entry, we can choose in p ways because there are p option, and also on the second entry we can choose in p ways. So there are p squared ways to choose any first column, but we need to consider that we are not allowed to take zero vector. So for the first column we are allowed to choose p squared minus 1, where the 1 is exactly coming from the zero vector. Okay. How about the second column? So we need to think, how can we make sure that the second column is not linearly dependent upon the first column? So the only way the second column is linearly dependent upon the first column if the second column is a multiple of the first column. And how many multiple of the first column? So when we chose the first column, so once the first column is chosen, okay, there are, so let's say the first column x, for example, is chosen. There are alpha x multiple of x. What I'm trying to say is, so multiple of x is of the form alpha x, where alpha can be any scalar from 0 to p minus 1, because we are in ZP, where alpha in ZP. So there are p choices of alpha. It means that there are p vectors which is linearly dependent to the first column, so that the number of ways we can choose the second column. First, we can choose any vector columns in p squared ways, but then we need to avoid all multiples of the first column, and there are exactly p multiples of the first column, so p squared minus p. Okay, so therefore the cardinality of GL to ZP is exactly p squared minus 1 times p squared minus p. Okay, and from this you probably know how to extend the argument for the general case for GLN. Okay, so before we discuss that, you might want to pause the video for a while and give it a try by yourself. Okay, so now let's discuss how about the cardinality of GL and ZP. Okay, so remember that for the first column we can choose anything but the zero vector. Okay, first column, but the first column consists of n entries. Okay, for each entry there are p choices of entry, namely 0, 1, 2 up to p minus 1. So therefore, if we don't restrict anything, then we have p to the power p times p times p n times ways to choose the first column without any restriction, right? But since we are not allowed a zero vector, therefore for the first column, we can choose p to the n minus 1 ways. Okay, how about the second column? Okay, for the second column, like what we did before, we are not allowed to choose multiples of the first column. Since the scalars, since they are p type of scalar, namely from 0 to p minus 1, then there are p multiples of the first column. Therefore, if we avoid all multiples of the first column, we can choose p to the n minus p ways. Okay. So once we have chosen the first, okay, for example, once the first up to the kth column have been chosen, then we need to think of how to choose the kth plus 1 column, right? So since we want to make sure that the k plus 1 column is linearly dependent to the first kth column, so we are not allowed this column to be a linear combination of the first kth column, right? So then we need to calculate the number of linear combination of the first kth column. So what is the linear combination of the first kth column? It is all expression of the form lambda 1 the first column plus lambda 2 the second column and so on up to lambda k ck. Okay, so we want to count the cardinality of this. Okay, now notice that for each alpha I can be chosen in p ways. So this one is in p ways, this one also in p ways, and this one also in p ways. So therefore the cardinality of all linear combination of C1, C2 up to Ck is exactly p to the kth power, right? So therefore we can choose any vector from p to the n possibilities except all linear combination of the first up to the kth column. And this kind of linear combination is exactly p to the kth. So therefore, the kth plus 1 column can be chosen in p to the n minus p to the k ways. Okay. So we keep doing that until we choose the nth column. And the nth column is p to the n minus p to the n minus 1 ways. So overall, the cardinality of GL and ZP is the product of all of this. This times that, and so on. Which is p to the n minus 1, p to the n power minus p to the n minus p squared, so on, p to the n minus, and the last one, p to the n minus p to the n minus 1. So that's all. So that's the cardinality of the GL and ZP. Okay, so that's all for today. Thank you for watching. See you again on the next video. Bye bye.